Professor John Coates needs no introduction. But here I will still go through the middle. So, Professor Coates made fundamental contributions in family approximations, Kurosawa theory, and paired L functions. His 1977 paper with Wiles was the first breakthrough to the conjecture of Birch and Swinton type. So it is really a landmark contribution to nodal theory. So Professor Coates was elected a member of the Royal Society of London in 1985. From 1988 to 1990, he served as the president of the London Math Society. In 1997, he received the prestigious Senior Whitehead Prize from the London Math Society. So I think I made my introduction brief. So the title of this talk today is the conjecture of the Birch and Swinton diet. Let's welcome Professor Coates.
Thank you very much, Winnie, and it really has been a great honor for me to have spoken at all these ICCMs so far today. What I wanted to talk about today is it's intimately connected with the conjecture of Birch and Swinton diet, but it's really a very first step towards trying to generalize to other families of elliptic curves the beautiful results of Yi Tian on the congruent number problem. And so let me begin by just talking about the question that one wants to settle in general. So let me take an arbitrary elliptic curve, E over Q, and if you're interested in the arithmetic of E, then we're interested in determining its group of rational points, E of Q, and I'm always going to write G of E for the rank of EQ. EQ, of course, by Mordell's theorem, is a finitely generated abelian group. And the problem with finding this group is our lack of knowledge about the Tate-Shafarevich group of E, which I'll call Shar of E. And by definition, it's the kernel of the map from H1 Q of E. Now, by this I mean of course, the Galois group of Q bar over Q, acting on the points of E with coordinates in Q bar. And then you look at all the locally trivial elements in here. So you look at the corresponding groups over the completions of Q at all places V, and this is the infamous Tate-Shafarevich group. And let me say immediately that it's always conjectured to be finite, but we have no idea how to prove it in general. But even if we knew the weaker assumption that there are no infinitely divisible elements in it, everything that I have to say from now on would be unnecessary. But the problem is we don't know that, and no one has ever been able to settle it. So this is what brings in the analytic side. And so I'm going to write LE of S for the complex L series of E. It's defined by the usual order product. I'm not going to write it down. And of course, after the work of Wiles and others, we know that there is it's an entire function now, and it has the usual functional equation relating its values in S and 2 minus S. And then what will be important for us is that there's a sign in the functional equation, WE, which is plus or minus 1, which can be computed by purely local means. And what we will be interested in will be the order of its zero. at the point s equals 1 in the center of the critical strip. Now actually what we're going to be interested in is the following infinite families of elliptic curves. We start off with one elliptic curve, and then I'm going to recall that, so I want to talk about the quadratic twists. This is the one way of getting an infinite family of elliptic curves over Q from a given curve. So let me take R to be any integer not equal to 1 and square free. And then I'm going to write ER for the twist of E by the quadratic extension of Q of join the square root of R over Q. So if you wrote your curve in the usual y squared equals a cubic form, this would be, then you would be looking at the curve ry squared equals the same cubic. Now this is again the elliptic curve over Q, and 50% of the time, if you look at its root number, we have the WER now, the root number for WER is plus 1, and 50% of the time WER is minus 1. And of course this root number determines the parity of the integer RE, which is what is important in what follows. Now the first theorem I want to state is the theorem of an old theorem due to the Morty brothers. And Bump, Friedberg, and Hofstein, which tells you that if you take any elliptic curve E over Q, then there exist infinitely many R. Such that the L series of E twisted by R does not vanish at s equals 1, and equally there are infinitely many R such that the L series, such that in fact the order of the zero of the L series of L E R of S is equal to 1. That there is a simple zero at s equals 1. And you see the significance of knowing there's a simple zero is that it tells you that in fact by an important theorem of, let me just say it in words, of Gross, Zagier, and Colley-Vargan, that the rank is 1. So that this is the only way we have at present of really proving the existence of points on the curve of infinite order without actually writing them down. Now the trouble with this theorem is that even though it proves there are infinitely many R with this property, it actually only gives a very thin, it tells you nothing about this R, essentially beyond the fact that it's an infinite set. And the whole idea of Tian's method is to show that there are many such R's, and in particular many such R's for which this is true. Now in his method, you can't, it's very curious that I'll be explaining the method as I go along, that you can't just look at the twists, at all of the twists, but you have to look at two sets of twists, which I'm going to call N of E, and then there will be an analogous set of twists P of E, and what we want is to prove the existence of a large, and I'll be quite precise when I say the theorem in a moment, infinite set of integers n. Now these integers could be positive or negative, by the way. Sometimes large, it's going to be large such that these n are prime to the conductor of E always. I'll always assume that. So C of E will be the conductor of E, this will precisely by the bad primes, with, in fact, the LE of NS having a simple zero. So these will all be, because we're looking for a simple zero, all of the elements in here will certainly have WEN equal to -1. They will all have root number -1. But, of course, some of the time, if we looked at N of E to be all the twists, they would have zeros of order 3 or 5 or possibly even arbitrary large order. So that's why we have to, I'll be specifying what this N of E is a little later. But now what's very interesting is that the analytic arguments to prove the existence of N of E, you have to use another set, which I'm going to call P of E. In fact, it's very closely related to N of E, of, again, twists. So these will be a set of positive integers, well, not necessarily, they will in our example, of integers m with m prime to C of E. The root number for these, WEN, should be +1. And the most mysterious thing, well, I'll specify exactly what this set is in a moment, but I want to, when we come to a specific curve, but they have to have the property, for reasons we don't understand why, conceptually, it just comes out of the proof, that in addition, if the L value, LE of M, 1, is not naught, then we have the Tate-Shafarevich group of En, the two primary part must be non-zero. It's a black magic thing, but it has to be. So in some sense, to generalize Tian's method, we are searching for these sets N of E and P of E that are closely related for any elliptic curve. But now I want to tell you at least a partial answer to this question for one more. So Tian looked at the curve y squared equals x cubed minus x. In ENs, of course, the curves y squared equals x cubed minus n squared x. And they're very interesting classically because the points on them, if there's a point of infinite order on this, is precisely when n is a congruent number in the ancient sense. So I'm going to describe now some joint work with Tian and two Chinese students, Dongxiong Li and Shuai Zhai, and myself. This gives a partial answer to this question and I think raises many other interesting problems for generalizing it, for the following curve. I'm going to take the curve E equals x naught of 49. This is the modular curve of level 49. So it's an explicit equation for it is given by y squared plus xy equals x cubed minus x squared minus 2x minus 1. Now we know the full story. It's like the congruent number curve. Fermat determined the full story of its arithmetic long ago, and for this curve it's well known too that E of q is just z modulo 2z, and it's generated at the point of order 2 has coordinates 2 and minus 1. In fact, it has complex multiplication by the ring of integers of the field q of square root of minus 7. It has char of E. Its Tate-Shafarevich group is known to be 0. And in fact, the reason why we know it's 0 is that its L series, LE of 1, has the value, the value is omega over 2, where omega is the least positive real period of the Néron differential on this curve. In fact, it has a classical formula, which I'm not going to write down for it, in terms of the gamma function. And it's the fact that this L function doesn't vanish that enables you to prove this. Now, it also turns out, because they'll be important to us, the following two fields, Q adjoin the coordinates of the two division points on E, is the field Q adjoin the square root of minus 7. And the Q adjoin the four division points, again, for reasons that for the moment we don't know why, but it plays an important role, and maybe for all elliptic curves like this, is it turns out to be the field, in this case, of course it contains the fourth roots of unity by the Weil pairing, and then the fourth root of the square root of minus 7. So for this curve, now I'm going to tell you what the set P of E you should take. And then everything will be determined by that. So the definition, P of E will be the set of all square-free positive integers P1 up to Pk, any number of prime factors, where each Pi splits completely in the field Q adjoin the four division. Now, of course, if you're not an algebraic numbers theorist, you might, somehow these sets of primes, which split completely in a given number field, are very important always for the number. And of course, we know by the Cheretarev's theorem that there's a positive density of such primes. And in fact, you can easily work out the beginning of them here, that the first few primes which split completely are 53, 113, 149, 193, 197, and so on. And now we're going to be interested in the, as I said, we know the arithmetic of E itself, but in the quadratic twists of E. So if you want an explicit expression, En is given by this explicit equation y squared equals x cubed plus 21 nx squared plus 112 n squared x for any integer n. This is the twist of E. So it's that family of curves that we now want to look at. So let me tell you the theorem that one can prove, and then I want to discuss the ideas underlying its proof, because that is the really original part of Tian's work. So the theorem is the following, and it's by it's, as I say, joint work with those 4 people I mentioned earlier, 3 people plus me. So I want to take, let n be an integer of the form minus p naught times n, where m is any element of this set P of E that I've just defined, this large infinite set, and P naught is any prime which satisfies the following conditions. It should be congruent with 3 mod 4. It should not be 7. And it should not be, it is a non-square and a non-square. Modulo 7. So this is a set we're going to work with. In fact, the set of such n's will be the set that I call n of it in this case. And so what one proves is the following, that assume that the ideal class group of the imaginary quadratic field Q adjoining the square root of n. Remember, n now is a negative number, so there's an imaginary quadratic field, has no element of order 4. Of course, it has lots of elements of order 2, for ideas going back to Gauss, because it's a highly composite square-free number. Then the conclusion is, then, indeed, LENS has a simple 0 at s equals 1. And so we know then that En of Q automatically has rank 1. And we know that the Tate-Shafarevich group of En is finite. This is all by the theorem. Once you know this, this follows by the theorem of Kolyvag and Rosaghier, but we get the slightly stronger statement, and char of En is finite of odd order. That's the curious thing. That even though we would use twists where the root number is plus 1 where the order is even, here for this twist it is odd. So the immediate corollary of this, of course, is that maybe I should put that up right here. Is you see, well, I'll just state it, that it's known that there are I guess even a positive density of discriminants of imaginary quadratic fields with this property that the class number, that the ideal class group has no element of order 4. But even from a simpler statement than that, you can see immediately this implies that for this curve E, if you take any integer k greater than or equal to 1, there are infinitely many twists with exactly k prime factors where the L function has a simple zero at S=5. This is exactly the sort of statement we would love to have for every elliptic curve. Okay, so now in the rest of my lecture, I want to try and explain why the proof of this is very different from what we knew before Tian's work. And I'll begin by explaining the ideas that go back to Heegner. It's a generalization of Heegner's work. And then we will see where they stop without his ideas, and then with his ideas we can go on. So let me right now, I'm going to first talk about Heegner points. So let me, on x naught of 49, so x naught of 49 is the modular curve where you divide the upper half plane by the congruent subgroup gamma naught of 49. My n will be an integer up there. So n is less than naught, and it has all those properties. And, well, don't let me assume at the beginning this hypothesis about the ideal class group. That will only come in right at the end of the argument. And so I want to write K of n for this field, this imaginary quadratic field Q adjoins the square root of n, and OK of n for its ring of integers. Now a key fact, a little exercise in quadratic reciprocity that I need to use, is that 7 splits in K of n. So we have, in other words, that 7 OKN can be written as P star, where they are distinct primes. Here, maybe I should call it P7. P7 star, follow my notes. Now, from the modular point of view, the points on x naught of 49 can be thought of as equivalence classes of isogenies between two elliptic curves, say E1 and E2, with the cardinality of the kernel of phi equals 49. That's what it would be from the modular point of view. So, following Heegner, we want to make the definition. In fact, I should say that Heegner never quite said it this way. This is really Birch who began to say it this way. But Wn now will be defined, it will be the Heegner point, it will be defined by the isogeny C modulo OKN to C modulo OKN, so this is capital N, times P7, I think one of the primes to the power minus 2. So that is the Heegner point we're interested in. Now, in fact, it's not just defined over the complex numbers, but the classical theory of complex multiplication tells us that it's actually defined over the Hilbert class field of Kn. So let me draw a diagram here that we want to bear in mind for the rest of the lecture. So Kn is this imaginary quadratic field, and then up here I'll have H of n, which will be the maximum unramified Arbidian extension of Kn at n. It's the Hilbert class field. Of K of n. And so this Galois group here, which I'll write as G sub n, we actually know by class field theory is isomorphic to Cn, which is the ideal class group of this field. Finite extension, this Galois group is isomorphic to Cn. And now, as I say, it's a fact that Wn is actually a point on E with coordinates in h of n. And so the natural thing is to take its trace on the elliptic curve, and so that would be the definition of the point u of n, which would be its trace from h of n down to the field k of n of Wn. So this is the Hager point we're interested in. Now the whole problem now, and this is where in some sense the classical theory stops, is that the big question is this point of finite order or not? And the whole problem is that the only way we know that it is finite order with our knowledge up so far is if the complex L function, LPNS, has a simple zero. And s equals 1. That's what the existing theory would tell us. But the problem is we don't know how to prove that it has a simple zero s equals 1. And we simply don't know, or we didn't know before Tian, how we should. In fact, what we're going to do is one's going to use an argument involving this Hager point and various other facts about L functions to conclude this eventually. Whereas up until now, one would have said, okay, we try and prove this analytically, but the analytic people don't know how to prove it. That's the problem for such families. Okay, so now one further word. That let me right now, just because you see I'm now going to be describing Tian's induction argument, so let me write my n, it will be minus P naught times P1 up to Pk, where Pi for 1 less than or equal to I less than or equal to K splits completely. In the field Q adjoining E4. So that's what n is, and now by Gauss's theory of genera, in fact, see there's a subfield here I'm going to call Jn that will play a crucial role, and it's the field that you get by adjoining to Kn the square root of minus P naught and the square root of P1 plus P1 up to Pk. In fact, it's rather easy to see that that has to be a subfield. It's an unramified Armenian extension. What's not quite so obvious is that this Galois group here, which is a subgroup of Gn, is precisely twice the ideal class group. And therefore, that extension, eventually we'll need that, but this extension will have odd degree precisely when the ideal class group has no element of order 4. Now, one other remark that I'm going to, we're looking at the points in EKN, and I'm most interested in the points that are called subgroup, which are called EKN minus. And by definition, this is the set of all points P in EKN such that tau of P is minus P, where tau is the non-trivial element of the Galois group of Kn over Q. So in fact, these are precisely, you can identify these points with En of Q, and that's where we want to eventually construct them. Okay, so now the crucial idea of Tian's work is the induction method, and let me say what it proves in this case. And then I want to talk about the ideas needed to prove. So the actual theorem that one proves is the following, that assume k is greater than or equal to 1. The case when k equals naught is in fact classical. It was done by Birch long ago. Then, in fact, un always belongs to 2 to the k minus 1 e of kn minus plus e of kn. This is a crucial step, which is really new, because as we'll see, I'll just say a word at the end, that once you have this statement, you can in fact use the same argument as essentially, it's a little more work, as used by Hegner and later Birch in special cases when k is 0, to conclude the theorem. The crucial thing is to be able to show that this Hegner point lies in this, as k gets large, it's very large multiple of ek and minus, and you don't care about it. Now, the very ingenious method that Tian has for doing that is to use an induction on k involving imprimitive Hegner points. They've always been there, these imprimitive Hegner points, but I think no one found any good use for them before. So let me quickly recall the definition and the key fact that emerges. So now let me define D of n will be the set of all negative divisors. So negative divisors of n, which are divisible by p naught. So you see, if you take an n dashed in D of n, we will again, it will have root number we of n dashed, will again have root number minus 1. It will be exactly one of the ones that you're looking at, but with a smaller set of primes involved. But now, if n is dashed is not equal to n, we can do the following. We can let chi n dashed be the character of the quadratic extension kn adjoin the square root of n dashed over kn. Now you see, because this field here, kn adjoin the square root of n dashed, will again be just a quadratic subfield of Jn. And so it lies inside the Hilbert class field, and so therefore we can make the following definition of the imprimitive Hegner point. Un n dashed will be the sum of the sigma in Gn of chi n dashed of sigma of Wn. So in fact, this, if I took chi n dash to be the trivial character when n dash is n, you see we again would have the new n, which would be simply my original Hager point un. And now here's the first key use of, I now want to explain, of L values. I'm going to prove that theorem. So if I have any n belonging to the set P of E, so now this is an M where the root number is +1, let me define its algebraic L value of EM1 to be L EM1 times the square root of n over the same omega infinity, the same real period of E as before. So this factor of square root of n here is just, it's the change in the period when you twist the curve. And then also let me write h hat for the canonical Néron-Tate height on Q bar, the absolute Néron-Tate height. And then the key fact that you prove is the following theorem. And I just have to state it. The proof depends on the fun. You apply the Rose-Sargé and Polyvargan theorem, which are partial results in the direction of the Berg-Swinnerton-Dyer conjecture. And so you get the following result. And assume that this Hager point, Nn prime, is not torsion. If it is torsion, it turns out it's absolutely harmless. But let's assume it's not a torsion point. Then un dash, which would be the Hager point that I defined for n, but for n dash, is not torsion. E of Kn dash has rank 1. And the crucial thing is that you can compare the height, the canonical height, h hat of u and n dashed over h hat of un is given by the following ratio of L values, namely its L algebraic En. I'm sorry, En over n dash. 1 over L algebraic of E1. So now these L values here, this is the heart of the method, are L values where the root number is +1.